Okay, so we have a physics PhD qualifying exam practice problem number 20 in the domain of statistical mechanics. So let's begin. Consider the one-dimensional Ising chain with periodic boundary conditions here. H equals that negative j, and then we have the sum from I equals 1 to n of that s sub I times s sub I plus 1 minus h, then times the sum from I equals 1 to n of s sub I, where s sub I equals plus or minus 1. So let's go over all of 6 components, A through F. A, construct the transfer matrix for the system. B, diagonalize the transfer matrix exactly and determine its eigenvalues. C, obtain the exact partition function z of n t h for finite n. D, calculate the magnetization m of t h as a function of temperature and external field. E, show rigorously why the one-dimensional Ising model has no finite temperature phase transition. And F, determine the correlation linked here, xi, t, and analyze its behavior as t approaches 0. Okay, so let's begin with letter A, constructing the transfer matrix for the system. Okay, so letter A here. So one-dimensional Ising model transverse matrix problem. So part A, the transverse matrix. H equals negative j, and then we have the times here the sum from I equals 1 to n of s sub I times s sub I plus 1 minus h times the sum of I equals 1 to n s sub I, again, where s sub I equals plus or minus 1. The periodic boundary conditions, s sub n plus 1 equals s sub 1. Let beta equal 1 over k sub b t. So what we're going to do here is split the field term evenly between the neighboring bonds with h equals that negative sum of I equals 1 to n bracket j s sub I times s sub I plus 1 plus h of 2 times quantity s sub I plus s sub I plus 1 close bracket. And then we have z equaling this sum here with this s sub I, this bracket here, and then this pi n, and this t sub s sub I, and then s sub I plus 1, where t sub s sub prime equals the exponential of this bracket beta j s sub prime plus beta h over 2 s plus s prime bracket. Pardon me if I'm like choppy today with whoops-a-daisy, sorry about that, with the way I'm explaining it. Sorry about that. So using the order s equals plus 1 minus 1, we're going to get this matrix T equals, for this first row, e to the beta j plus beta h, e to the negative beta j. And here, e to the negative beta j, e to the beta j minus beta h for the second row. And that's our t equals. That's for letter A. For letter B, what they want us to do is diagonalize the transfer matrix exactly and determine its eigenvalues. Okay, so let's see what we have here. For the eigenvalues for a 2 by 2 matrix, this lambda plus minus equals a trace t over 2 plus or minus, that's square root of the quantity t11 minus t22 over 2 squared plus t12 t21. And that's all underneath the square root. Okay, and now here, we have the trace t equals 2e beta j, hyperbolic cosine of beta h, and then we have t 11 minus t22 over 2 equals e beta j, hyperbolic sine of beta h. And t12 t21 equals e to the negative 2 beta j. Now from here, what we're going to get is that lambda plus minus equals e beta j hyperbolic cosine of beta h plus or minus the square root of e to the 2 beta j hyperbolic sine squared of beta h plus e to the negative 2 beta j. Or lambda plus minus equals e to the beta j times this quantity hyperbolic cosine of beta h plus or minus the square root of hyperbolic sine squared of beta h plus e to the negative 4 beta j. So that's letter B. Letter C, we want to obtain the exact partition function z of nth for finite n. Sorry about that. So exact partition function because of periodic boundary conditions, z equals a trace of that t to the n. So z equals that lambda plus n plus lambda minus n. Some people would pronounce that differently. In thermodynamic limit, n approaches infinity, since lambda plus is greater than the absolute value of lambda minus. So this z is approximately equal to this lambda plus n. And the free energy per spin is this F equals negative k sub bt ln lambda plus. Okay, so that's letter C. Again, some people would pronounce this differently, and I apologize if the way I'm going through this, I'm going in and out, and it's not as fluid, and it's like breaking up a little bit. Sorry about that. I'm not sure how the video is coming out. Letter D, magnetization. So what they wanted us to do for letter D is calculate the magnetization m of th as a function of temperature and external field. So for part D, the magnetization per spin is m equals 1 over n, and then the partial derivative of this ln of z with respect to beta h. And in the thermodynamic limit, m equals that partial derivative of ln lambda plus with respect to beta h. We're going to let x equals beta h, and d is going to equal the square root of hyperbolic sine squared x plus e to the negative 4 beta j. So then from here we have lambda plus equals e to the beta j times that quantity hyperbolic cosine plus d. And now from here, our m equals hyperbolic sine x plus this quantity here, hyperbolic sine x cosine, hyperbolic cosine x over d. And that's going to be divided by the hyperbolic cosine x plus d. So simplifying that, m is going to equal hyperbolic sine of beta h over the square root of hyperbolic sine squared of beta h plus e to the negative 4 beta j. Okay. Now from here, what we could conclude is the total magnetization is m equals n lowercase m, and at zero field h equals 0. So m equals 0, lowercase m equals 0 for any finite t being greater than 0. And that's letter D. And now for letter E, what they want us to do is show rigorously why the one-dimensional Ising model has no finite temperature phase transition. So from here, no finite temperature phase transition. A phase transition, sorry about that, would require a non-analytic free energy, but for finite t is greater than 0, that lambda plus equals e to the beta j times bracket hyperbolic cosine of beta h plus the square root of hyperbolic sorry excuse me, sorry. Hyperbolic sine squared of beta h plus e to the negative 4 beta j, close bracket. N is analytic in t and h. And since e to the negative 4 beta j happens to be greater than 0 for any finite t. So from there, f equals negative k sub b t ln lambda plus is analytic for all finite t greater than 0. So there is no finite temperature transit. There is no finite temperature phase transition in the 1D Ising model. And we could say at h equals 0, m equals 0 for every finite t greater than 0. So there is no spontaneous magnetization at finite temperature. Sorry about that. My voice is going, having some trouble pronouncing. And letter F. Letter F, they want us to determine the correlation length here. That's psi t. Okay, so and analyze its behavior as t approaches 0. So correlation length at 0 field h equals 0. So lambda plus equals e to the beta j plus e to the negative beta j equals 2 hyperbolic cosine of beta j, and lambda minus equals e to the beta j minus e to the negative beta j equals 2 hyperbolic sine of beta j. The spin correlation behaves as follows, with these expectation values being, so this expectation value of S naught SR minus expectation value of S naught, expectation value here of S sub R, proportional to the quotient of lambda minus and lambda plus raised to the R power. So this quotient lambda minus over lambda plus raised to the R power, that is e to the negative R over xi, and inverse xi equals negative log, or negative ln, absolute value of lambda minus over lambda plus. Some would say lambda sub minus lambda sub plus, but and at h equals 0, lambda minus over lambda plus, that equals the hyperbolic tangent of beta j. So our xi equals negative 1 over ln of that hyperbolic tan of beta j. So for t is approaching 0, for t is approaching 0, beta j is approaching infinity. And then hyperbolic tan of beta j is approximately equal to 1 minus 2 e to the negative 2 beta j. And using ln, 1 minus epsilon is approximately equal to negative epsilon. So ln hyperbolic tangent of beta j is approximately equal to negative 2 e to the negative 2 beta j. So our psi is approximately equal to 1/2 e to the 2 beta j, psi approximately equal to 1/2 e to the 2j over k sub bt, where t is approaching infinity, and as t is approaching 0, rather. And over here, as t is approaching 0, beta j equals j over k sub bt, that's approaching infinity. And we can conclude here further that the correlation length diverges only as t approaches infinity, not at any finite temperature. Whoops, sorry about that. Let me just finish that up. So the correlation length here diverges only as t approaches infinity, only as t approaches 0, I'm so sorry, not at any finite temperature. Okay, so sorry about that. So thank you very much and have a great day.